So let's have a look at mechanical waves. There are three things we're going to consider. First, let's describe the features of a mechanical wave. Let's ask the question, what does the speed of a mechanical wave depend upon? And how does a pulse differ from a wave? So there's some features we want to look at. First of all, vibrating objects act as sources of a wave. Vibrating object could be something like a tuning fork, vibrating water in which the water is moving up and down, propagating the energy through it. Perhaps a slinky, producing a pulse in a slinky and having the energy travel the full length of a slinky. These would be considered vibrating objects. Waves consist of oscillations that move without carrying any matter with them. So in the case of a vibrating slinky, when you produce a pulse, the slinky itself doesn't travel the full length of the slinky. All the coils remain in their respective positions, but the energy does travel through the slinky. A mechanical wave is formed when mechanical energy is given to an object or medium, causing the particles of the medium to oscillate in simpler harmonic motion. So when you flick a slinky or a rope, you're putting energy into that rope or into that slinky. That produces a wave that moves through the medium. The slinky itself would be considered the medium in that case. So let's look at a rope or slinky. A slinky is a great model to discuss wave motion. It's very easy to envision, and it's something that we have around our laboratory that we can have access to. So if we take a slinky, represented with this red line, and we move it up and down with our hand, that up and down creates what we call a disturbance, and that would be the energy that we're putting into that slinky. Now, if we select one part of the slinky, perhaps we tie a ribbon to the slinky to show that that part of the slinky is actually only moving up and down. That would be the velocity of the up and down motion. But the wave which is created is going to be moving with the slinky. And that would be the energy traveling from one end of the slinky to the next. And that would be an example of a mechanical wave. So, to reiterate, to produce a wave on a slinky, the hand creates an up and down disturbance that results in a wave moving at a right angle away from the disturbance. So notice that to create a wave, we move the hand up and down, and the wave itself travels at a right angle to that up and down motion. Another example, which you are no doubt familiar with, is a water wave due to a pebble dropped into a undisturbed surface of water. So here's a top view. If we were to drop a pebble into the water, what would happen is you would get a series of concentric circles that would move or propagate outwards. So each one of those circles would be the top or the crest of the wave. And that waveform would just move outward. Now, if we were to take this wave and make a cross-section of the wave and look at it sideways, what you would see is this is where the pebble would be dropped in, and the water would be pushed outwards. So this first circle right here, these two crests represent a cross-section of that circle. And then this would be the second circle, and so on. So the waves actually propagate outward away from the disturbance. So let's look at a diagram of a wave and note its features. Our reference point, of course, would be the equilibrium point, and the wave would move up and down above that equilibrium point. This peak right here, I don't have this labeled, but this peak right here is called crest, the crest of the wave, so add that to your notes. And this valley here is known as the trough, T-R-O-U-G-H, trough. So we have 1, 2, 3 crests in our diagram and 2 troughs in our diagram. Now the way we measure the size of the wave is typically we would say that we measure it from peak to peak or crest to crest, and we denote the size of the wave with the Greek letter lambda, and that means wavelength, the length of the wave. Now lambda can be measured really at any point along the wave. It's just important that we have a complete wave. So if, let's say, we pick that point right there, the upswing of the wave, well, the next time we encounter the upswing of the wave would be the start of the next wave. So this wave would start here, we're going up, then we're going down, and then again, on the upswing, that's where the wave would end. So between these 2 points, that would represent lambda measured in a different fashion. But most often we would just pick from peak to peak because that's very easy to see. So A means amplitude, and that would be the height of the wave, or you could say the depth of the trough. This would be positive, that would be negative. Lambda, as we mentioned, that's Greek letter lambda. That would be the wavelength, and that's the distance between crest to crest. And now the period of wave is how long does that wave take to travel a particular point. So if I have a reference like my finger here and the wave is moving from left to right, well, the time it takes from one crest to travel to the position of the forward crest, so the time from crest to crest, that would be the period. Now, of course, we know from our previous studies that there's a relationship between period and frequency is equal to the reciprocal of period. Now, wave velocity, how fast this wave is moving, we know that velocity is distance divided by time, and distance here would be the wavelength, and the time would be the period it takes for that wave to travel. So, and that of course applies to a sinusoidal wave, a wave that has that sinusoidal pattern. So velocity is equal to wavelength divided by period, or if we want to write it in terms of frequency, the velocity is equal to wavelength times frequency.